This article is part of my PhD program, and then adding some values to the steganography field. So as the title says, multi-image steganography using distributed LSB algorithm, the proposed algorithm, and secret text recovery on Stego image corruption. We'll break down this title and then see what it is over the slides. For now, this is the title that I'm going to present, and with my guide. So let me give you some introduction on steganography. Steganography, which means that it is a covered writing or hidden writing. It was coined from a Greek term, and it was earlier used by many of our kings in the past. Even the Herodotus, the historian, says in 440 BC, this technology is used. You might be getting confused this technology with cryptography. We can compare and contradict. So cryptography is a technique where you will give a message and then you will encode it into a different format. It means you will encrypt it so that whoever intrudes it, whoever sees it in the transmission, they will not be able to understand that message. But for sure, we know that there is something is going and something is fishy, means which is encrypted. Some content is going if they open that encrypted file, right? So whereas if you take on contrary the steganography, we are hiding our secret message, like how we encrypt in the cryptography. We are hiding our secret message in another file, another digital file. Means, let's say, for example, adding your secret text inside an image file, inside a movie file, or inside a music file, and send it to the receiver. And during the transmission, nobody will be able to suspect the file or suspect the transmission or the communication. I mean, they will not find anything fishy there. So it means that the message being transferred itself kept very secret. On a plain plain site, you will not be able to see it. On a general computer firewalls, they will not be able to identify it. So it's a communication technique evolving from the past decade in the computer science field. So as we see in the right bottom figure, so this is a technology used by the king. Means he will shave the head of a slave, write the secret message, wait for a week or two to the hair to grow, and then send it to his sub kingdoms. And then once he reaches the small king, whoever is ruling a region of the bigger kingdom, he'll shave the slave's head and then take the message. So this is how this is an analogy to the steganography, how we have implemented in the computer science field. I mean, here the focus is mainly on the image steganography, but the concept-wise, steganography means sending a content which is hidden in another for digital file on a plain site or on by using a regular firewall, people will not be able to identify. So that's the steganography strength. Whereas cryptography, you will still see there is something encrypted and we can try to decrypt it. And whatever I told, I just put it in a flow. Here, there are three parts. One is sender, the middle one is communication channel, and the receiving end, where the receiver will exist. So if you see the sender, he will encode the secret text in a cover image. The image which is being used to hide for the secret text is called cover image here, which once you encode that, we will call that as a Stego image. So cover image plus secret image equal to Stego image, means steganographed image, where we, in analogy, in cryptography world, we tell that as a encrypted file. So that will be transferred in the communication channel. So once the receiver receives it, he does the vice versa what had been done in the sender side, and then decrypts the, decodes the message, not decrypt. Okay. So this is kind of pictorial representation. For example, you take a cover image, you convert your secret message in binaries using the embedding function. You embed it, and that will be called as Stego image, and send it through network. And then at the end, the extracting function will give you the what is the hidden text. Okay, so for example, if you take a picture, I mean, when you read it in a binary format and extract certain bits and convert those certain bits into a text file, then you will get the original secret text what was sent by the sender. So it's a covered communication technology. So based on the file type that we use for the steganography, we can categorize it like it's a text steganography, image steganography, audio or video steganography, or even protocol steganography. So the types of steganography depends on the type of cover file that we use for hiding the secret text. These are all the major types. And before we get into how this works, let's talk about these few image terminologies or steganography terminologies. So if you take any picture, any digital image, we will represent it in the resolution or the dimension x and y, right? So 600 into 800, 800 into 600, or 1920 into 768. So, which means that it represents the number of pixels that are being used. Pixel is a very tiny particle of a digital image, which can be represented in the binary format. Means if you take it is like our two-dimensional matrix in mathematics or in computer science world. You take it and represent each one of the cell as a pixel. Okay, so if you so from this slide, the takeaway is our digital image is being boiled down to multiple pixels. Okay, so if you take the color of the nature of the pixel, how the color is represented. So we all know that red, green, and blue with the various mixer proportions, pretty much we'll get all the colors, human observable colors. So each pixel uses 3 bytes of data. Means if you want to represent a pixel, it needs to have 3 bytes of data, one for red, one for green, the other for blue. That's what you are seeing in the picture. Means this cat can be filtered into multiple planes like red, green, and blue. And this is the this is one of the color model which most of our electronic devices uses. And as I said, see, consider the picture as a two-dimensional matrix, and each matrix location means the index values that represents 3 bytes of data. And if you see here, the what is the combination of red, green, and blue? It is in the binary format. Means red has some value as 218, and green has 150 as a value, and blue has 149, which gives the color that is given here. So keep that in mind. So we kind of saw a digital image can be boiled down to pixel, and a pixel can be further boiled down to 3 independent bytes of RGB color model. Okay. So when you change the a byte contains 8 bits, which has various values. For example, if you take the rightmost bit, which is which represents the value 1, and that is called the least significant bit, means the significance is less there. If you take the last one, means the leftmost one, it represents higher value. Change in the least significant bit, means rightmost values, will not have much difference when you see the picture. Whereas if you change the most significant bit, which is leftmost, for example, if you change this 1 to 0, the value 1 to 0, then it will have tremendous effort. I mean, it is like half of the value, right? Shifting the value to shifting half of the value to something else. Okay, so we will see much of the difference. That's the takeaway here. So to continue to this, and as I said, uh, changing the rightmost bit means the least significant bit will have lesser effect in the picture. The leftmost one, most significant bit, will have more effect. Okay. For example, I told you, right? I mean, this value, if I change 1 to 0, then it will have lesser effect. Means what I'm going to do is I'm going to cut all of this value in red, green, blue. I'll read each and every pixel and then change only the least significant bits, and 1 to 0 or 0 to 1. For example, if I want to embed a value called A, which is ASCII representation is 65, I need to embed like 100005. Okay, for example, it is 0001 and 001, right? So what I'll do is I'll take the first bit and then put it here, and I'll take the next bit and I'll put it in the next location. So I'll take the next one and put it in the next location. This will be like your um, least significant bits of all those pixels. Okay, so yeah, to represent it in the numerical form, for example, if I want to embed this value 10010101, then I'll take the pixels like this, and then I'll change only the least significant bits. You see, uh, if you see the bold ones, whatever I am trying to embed, that will be here 10010101. Okay, so this is called the least significant bit steganography algorithm. This has been already introduced. I'm just explaining for us to understand better when I propose my model. So this is same whatever I have told. For example, if you take 1024 into 768, which will occupy in bitmap format 786432 bits, which means that it is 96 KB if you use the bitmap format. Okay, and we saw these algorithm, and what are the present limitations on these communication algorithm, means LSB algorithm, is the amount of secret text being embedded. For example, if my cover file, image file is 1 MB, I cannot embed 2 MB there, or I cannot embed 1 MB of secret text into the cover image, because the more the data that I insert, it will degrade the quality of the picture. So sometimes we will be able to visibly recognize, manual eye itself will be able to visibly recognize the changes. Means then the we can the intruder or the people whoever is watching the channel, they may get suspicious on the data being transferred. So one of the limitation is amount of secret text being embedded. And if say let's say someone attacks the let's say some hacker or some intruder does this man in the middle attack for the images being sent over the communication channel, there as of now there is no provision to figure out whether the image is already went through a Steg analysis. Okay, Steg analysis is the process of analyzing the suspicious images, steganographed images, and try to decode. It is something like the cryptanalysis in the cryptography world. You take the encrypted text and then try to decrypt it, and then uh, whatever you are trying to do with the encrypted text, with the focus of getting the original text in the cryptography world, right? That's called cryptanalysis. Similarly, if you take a steganographed image and try to take the content away and try to build the secret text from that Stego image, then that is called um, steganalysis. So if somebody has, let's say somebody is sending like secret text is deposit so and so amount to this account, some intruder or hacker sees that and then changes it to something else, and then sending it, then he will benefit. The hacker will benefit. Um, the, the the real-time use case of this technography technology is, for example, let's say it's being used in medical field um, for the images, medical images that we take. For example, if you send a scan report and then you also embed watermark kind of thing. You also embed your details in it. I mean, this is the patient name. This is taken at so and so time, and this is, I mean, verified by so and so radiologist or physician or whoever it is. So you kind of embed some metadata using this technology, and if somebody wants to tamper that, uh, that that is called man in the middle attack. Okay, and let's say I'm sending hello world, for example. I mean, for the discussion's sake, if somebody wants to change that hello world to hello sun or hello star, um, then that is not the message sent by the sender, right? So here, the secret text integrity is not being preserved. Okay, so that is one of the limitation in the current algorithms. And and let's say I'm sending a message, and kind of while in the transit it got corrupted, and there's no way to recover the secret text. Okay, so that is called the Stego image corruption. So the, the proposal here is we are going to distribute the content, distribute the secret text into multiple files, and if one of them are being attacked by any hacker, or we are or one of the image got corrupted, we will be still able to get the original secret text using the proposed algorithm, and I'll walk you through. So this is pretty much, I mean, a detailed view of the framework that what I am building. If you see the encoding part, we will encode the cover image. Means I'll take multiple files, and the secret text will be stored in multiple image files. Okay, and for saving the space in the saving the space in cover image, I'm also using the compress technique, which is already proposed technique in the past. So I am leveraging that, and then this is being sent as a multiple files in the network. Once it goes to the network, let's say um, one of the hacker or some streak analysis attack says that or corrupts this file. Okay, let's say here we are receiving only 2. Okay, then how we are decoding it here, the image recovery. That's what my proposal. This is overall the framework. but I'll walk you through on the table how I am getting or how I am regenerating the values which are corrupted in the third image. And this is a flow chart. I think we can directly go to the example so that you will easily understand the. We have already seen the flow and the concept. You will be able to straight away correlate this. For example, let's say I am going to send the hello world text. Okay, and this is the text that I am going to send, and uh, H in ASCII is 104, and 104's binary equivalent is this 01101, and I am dividing this and embedding this in uh, five different images. Okay, so the first four images will have 0110 means the two bits from here. Okay, so it's divided like that, and then if you see the last one, this is for our redundancy, means for the additional security. XOR function of all this, all the four value is stored here. Okay, if you take a, we know that XOR table, right? If it is a 1 1, it is 0. If it is a 0 1 1, 1 0 1, again, if it is 1 1, it is 0. Means we do a binary bit manipulation and find out the XOR value and then store that value as a store that value in the LSBs of the fifth image. So how this redundancy helps us on recovering the original content? That's the example that I had given here. For example, let's say image 3 goes for a task, or it got corrupted, or it is not received by the receiver. Not necessarily image 3 alone. We can take any of the images and then remove from this table and then regenerate the value. And if you take this working example, I am not taking the third one. If you do a 0 1 XOR, it is 1 1 0 again 1 1 0 again 1. That's the value that we are getting as a first digit here. And 1 0 it is 1 again 1 0 it is 1 1 1 it is 0. So we have got this 1 0. Okay. So similarly, we can recover all other bits in the absence of or the occasion of where the image 3 or any other image got corrupted during the communication or went through the steganalysis attack. So this is the proposal, and yeah. So I've also integrated the. How do you know that this value is not the right value? How do we detect this image is already corrupted or it went through the cryptanalysis attack? So for that, I use this checksum technique, MD5 checksum. So using this, I mean, before I embed the secret text, I'll also calculate the MD5 hash value and then store it as part of the transmission. And in the receiving end, I will just read the primary files, first four files, and then get the secret text, calculate the hash, and then compare that with the hash being sent in the header. If it not matches, it means that it is corrupted, and if it means it is not equal, I mean these two are not equal, it means that it got corrupted. Then I'll go ahead and then do the image recovery. So what are the advantages of proposed methodology with the existing legacy technologies? There is no digest inclusion, which is a novel here, and capability to identify man-in-the-middle attack. Earlier algorithms won't tell you that it went through attack, but using the proposed algorithm, we'll be able to figure it out. And yeah, and if it yeah, data integrity check, which was not there, and then random. Okay, while storing the uh, secret text values, we are not storing it in the same order how the image appears. We are storing it randomly and using a pseudo random number seed, and then regenerating the random numbers using pseudo random number key, and then reading in the same order. So if at all, if the hacker does not know about the pseudo random number, they'll not be able to interpret the value. So adding security to this. Okay. Any questions?